So let's read the problem. The problem says we have a function from this interval to r, and it's a non-decreasing function, and this is the property that we will use. It's the most important property we'll use in the solution. It's a non-decreasing. That's where you have to focus. A non-decreasing function f, and we have to prove that this inequality always holds for non-decreasing function. There is nothing special about this function other than it's non-decreasing. Our function f, which is from 0 to infinity, this holds true for all x, y, z which are positive and satisfy this condition: y is greater than x and z is greater than y. So basically f is a function from positive real numbers to real numbers, non-decreasing, and you have to prove that it satisfies this inequality with restrictions on x and y in this sense. So at first glance this inequality may seem daunting, but it really is not, and the solution is not very difficult. Okay, let's begin with the solution. Okay, so I have y to z and I have x to z. What I would like now is to break it to I would like to break x to z to x to y, then y to z. A bit of rearrangement is always advised to make some changes to play around with the problem. So a bit of rearrangement is always advised. So we'll do some sort of rearrangement, and that rearrangement is to break this x and z and to see how can we rewrite this inequality, and we do it in this way. It's y to z fu du is greater than, first I'll take it from x to y, then I will write z minus y times y to z. Okay, so now I would like to club these two together, and then I would get you know what this sign means? It means from, I'll tell you what it means. Let me just write this step. So I would have y minus x y to z is greater than z minus y integral from x to y fu du. Okay, so we have reduced our original problem to this form. Okay, what does this sign mean? This means from this inequality we can come to this inequality. This implies this, and from this inequality we can also get back to this inequality. This would imply this. So this implies this, and this also implies this. See, both way around. So that's what this symbol means. Okay, first we broke down this to this, and here also can use this if you want to write the original inequality here, and then this would be the second step, and then this would be the third step. Okay, so we just have to prove this inequality now. If we manage to prove this one, so from this one we can imply this, and from this we can imply the original one. Okay, so our focus is now this inequality. There are two ways to prove it now. You may like one more than the other, or you may like both the equal amount. We'll see. Let's look at the first way. Okay, how would we begin? We'll begin like this. we will use the fact that it is non-decreasing. That's what I told you. Whenever you are solving any problem, try to focus on the uh, speciality in that problem. Like in this problem, what is special about our function? Our function is non-decreasing, so you try to use this fact. Okay, so how can we do this? uh, this thing is greater than, what can you say? Can I say it is greater than y minus x and integral from y to z f y du? Can I say this? I think I can, because these two are same. If we can remove this for now, this is true. This integral is greater than this integral. The reason being that this fu will take values between y and z, which is greater than and equal to fy, of course. The values that the function f takes between y and z is greater than fy. Reason being, it's not decreasing, that is increasing. So we have taken, among the values that the function take between y and z, we have taken the smallest value, that is fy. That's the reason why this integral is bigger than this integral. And we've multiplied y minus x to both sides, so got this. Okay, now this thing is equal to y minus x. We'll evaluate this integral. Since it's a constant, we can take it outside, and then we would have this. You just, if you take it outside, we'll be left with 1 here, and the integral from y to z 1 du is z minus y. That's it. And this f y is taken outside, which I have written here. Okay, now we'll look at this carefully. Now what can I say about this? Now what I'll do is I'll rewrite this in this form: y minus x fy, and I will write this in this way. Y minus x can be written as x integral from x to y 1 du fy. It's right, because its integral is just this. Okay, now these all are equal. This thing is greater than this, and this is equal to this. This again is equal to this. This is equal to this, and this, what can you say about this? Now can I say that this thing right here, which I've written this, I will rewrite this now. So okay, so from here I can say, I will rewrite this: y minus z integral from x to y 1 du fy. Yes, fy. Can I say this thing is greater than or equal to z minus y x y fu du? Yeah, this one. Can you see why? Because if you take away these things, because these we can just cancel them out, here I can take this fy inside. So let me rewrite in this one more way, so that it will be much more easier for you to see that xy fy du is greater than, . . 。  . 。 . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . Okay, so the reason why this integral is greater than this one is we've taken fy is the greatest value of f that f can take between x and y. So, and here fu takes a value between x and y, all the values between x and y. So the value fy is greater than all the values that fu can take. So that would imply that this integral is greater than this integral, and then that would, we can multiply both the integrals by z minus y. Z minus y is positive, so the inequality sign remains the same, and that's how we got this. But we know that this thing right here is equal to this thing right here, and this thing right here is equal to this thing right here. They are the same, and this is equal to this is equal to this, and this is equal to this. So now from this, can I say that I can simply say, right, I think my problem is solved. This is greater than this is all equal, this is equal to this, and this is equal to this, and this is greater than this. So I think from here I can say that y minus x, which is this thing, I'll write this thing now here, is greater than this, which is what I had to prove. And I'm done. If you want to see it in one shot, you can do that. Here is it. Yeah, here you can see all the steps in one single screen. Now you may want to tilt your screen, that would be uncomfortable. Now moving to the second method. The second method is also very much similar, not very much similar. Okay, we want to prove this, right? And this was our first way, and if let's move to second way now. Second, what I'll do now is I'll bring this bracket right here, and I'll bring this one right here, and I can do that without changing the sign of inequality because both of them are positive. So I would have this with me then. Integral from y to z fu du, and here I would have z minus y greater than x to y fu du, and then I would have y minus x. Okay, now there is a theorem of mean value theorem of integrals. I would just insert it on the screen. You can see it on your screen now. And using this theorem, I can say the theorem is for continuous function. In this theorem that you see on your screen is for continuous function f, but my f is not continuous here. So if my f was continuous, I could have taken this, but now I would have to take just c1, because since f is not continuous, so I'm not sure whether my functions attain this value or not. You can understand what I'm trying to say when you read the proof of the mean value theorem. If you have a good command over mean value theorem, it should be easy for you from here on. Alright, so this integral right here is equal to z minus y and a constant c1. And what is special about c1? I'll tell you what is special about c1. I'll write it in a while. So this integral right here is equal to this, and in denominator I already had z minus y, so I'll keep it like this. and in this integral would be equal to y minus x c2 and y minus x right here. Now what is c1 c2? I'll tell you now. Now c1 belongs to fy comma fc, and c2 belongs to the interval fx comma fy. Okay, so from here I will have c1 is greater than equal to c2. So what I've basically done is, you can see this was this symbol, we have to prove this inequality, and this symbol would continue. I can again say this, that from this step I can go back to that step, and from that step I can come back to here. So it's enough to show this inequality, and this symbol will continue throughout. It's enough to show this, and it is enough to show this. So if we can show this, then our problem is done. But this thing right here is what obvious trivial, because you see my function is non-decreasing, that is increasing. So then this c1 lies between these two values. This is greater, so since it is increasing, so my function is increasing, I would have this, right? And c1 lies somewhere here between fy and fg, and c2 lies here between fx and fy. So c1 lies somewhere here, c2 lies here. So c1 is naturally greater than c2. So that's what we have written here, c1 is greater than c2. So this thing is trivial. You can give the reasoning for this, and you have proved this. And since you have proved it, this would imply this, and this would in turn 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 imply this. So it's all backwards here. So I think the problem is done now, and yes, both ways we have done. Yeah.